Welcome to our thermal analysis series. Today we'll explore how differential scanning calorimetry, also known as DSC, helps scientists understand how materials behave when they are heated or cooled. This powerful technique allows us to study the hidden thermal properties of materials used in pharmaceuticals, polymers, food, and metals. At its core, DSC is a thermal analysis technique that measures how much energy a material absorbs or releases when it is heated or cooled. It works by comparing a sample to a reference material under the same temperature conditions. You can think of DSC as a highly sensitive thermometer with extra powers that can detect tiny heat changes inside a material. DSC is widely used in pharmaceuticals, polymers, food science, and metallurgy to study material stability and behavior. DSC works by comparing the energy required to heat a sample and a reference material at the same rate. Both the sample pan and the reference pan are heated together. If the sample undergoes a change, like melting or crystallization, it will either absorb or release heat. This difference in energy between the sample and the reference is recorded and displayed as a curve called a thermogram. Endothermic events, such as melting, appear as peaks on this curve. First, the instrument heats both the sample and reference pans at a controlled rate. It continuously measures the difference in heat flow between them. These measurements are converted into a thermogram that shows where thermal events occur. The system has three main parts: the sample holder, where the test material is placed; the reference holder, which usually contains an empty pan or an inert substance; and sensors and heaters that precisely control temperature and measure heat flow. A DSC thermogram plots temperature on the horizontal axis and heat flow on the vertical axis. This curve reveals important thermal events inside the material. Endothermic peaks indicate that heat is being absorbed, such as during melting or a glass transition. Exothermic peaks indicate heat is being released, such as during crystallization or curing reactions. By analyzing these peaks, scientists can determine how a material responds to temperature changes. Several important thermal events can be observed in a DSC curve. The glass transition temperature, or TG, is when an amorphous material becomes soft and rubbery. The melting temperature, or TM, is when a crystalline solid absorbs heat and turns into a liquid. Crystallization temperature, TC, is when a liquid or amorphous material solidifies and releases heat. At higher temperatures, oxidation or degradation may occur, appearing as additional peaks on the curve. DSC is not just about analysing curves, it solves real-world problems across many industries. In pharmaceuticals, it is used to check drug stability and detect impurities. In polymers, DSC helps determine melting points and crystallinity. In food science, it studies fat melting behaviour and starch gelatinization. In metallurgy, DSC is used to analyse phase transitions and alloy behaviour. By understanding thermal behaviour, scientists can predict how materials will perform in real conditions. To get reliable DSC results, attention to detail is essential. Always use the correct sample mass. Too much or too little material can distort results. Ensure good thermal contact between the sample and the pan to avoid air gaps. Choose an appropriate heating rate. Slower rates reveal more details, while faster rates may hide subtle transitions. Regular calibration using standards like indium ensures accurate temperature and heat flow measurements. Small errors can significantly change the thermogram, so precision is key. DSC offers several important advantages. It is fast and easy to perform, provides both quantitative and qualitative data, and is often non-destructive to the sample. However, DSC also has limitations. It cannot always identify the chemical nature of a transition. Results are sensitive to sample preparation, and small transitions may be missed if the heating rate is too high. Next time you see a DSC curve, remember it is more than just a line. It is the heartbeat of the material, revealing its hidden thermal behaviour. DSC helps determine melting points, glass transitions, and crystallinity. It bridges the gap between theory and real-world material performance. And it supports scientists across multiple disciplines to design better drugs, plastics, foods, and metals.